All right, good morning. Welcome, everyone. Thanks for coming to the session, Improving HDFS Availability with Hadoop RPC Quality of Service. My name is Ming Ma. I'm a software engineer at Twitter, working on improving Hadoop reliability and scalability.
I'm Chris Lee. I do pretty much the same thing at eBay.
In this talk, Chris and I will walk you through the diagnosis of name node congestion and share with you how we go about solving the problem. At Twitter and eBay, we run Hadoop at large scale. We have clusters with thousands of nodes running tens of thousands of jobs per day. For example, at Twitter, we have a cluster with more than 6,000 nodes, launching 20,000 jobs and 20 million young containers each day. These jobs have different characteristics. Some are heavy on memory and CPU, others are network I/O intensive. Some are production jobs with strong SLA requirements, others are ad hoc experimental jobs. While MapReduce still represents the majority of our workload, people have been running new type of applications on Yarn to support interactive query, iterative machine learning, and other scenarios. So essentially, we are supporting Hadoop as a multi-tenant service for mixed workloads. An important aspect of multi-tenant service is performance isolation, so that different applications can run in predictable fashions without being impacted by others. Over the years, the community has made major improvement in this area from both architectural and feature enhancement point of view. And here are some major highlights based on our experience. At the compute layer, we rely on Yarn to manage cluster resource allocation for different teams. But the allocation model is mostly based on memory. We are starting to experiment CPU-based isolation and scheduling. And just like memory and CPU, network is another resource shared among all the users. And there's ongoing work at Yarn layer to provide network-based isolation and scheduling. For us, there's a specific use case, which is to manage the expensive cross-data center network bandwidth. And the solution we use is based on the DSCP bits in the IP header. It allows us to tag HDFS traffic with different priority levels, and then have routers apply quality of service accordingly. Another useful feature is HDFS federation. We use that to partition the global namespace into several name nodes so that each name node has less load and smaller memory footprints. It not only allows us to scale the cluster, but also provides some degree of performance isolation because hit on one name node won't impact the others. Lastly, running business critical application in a dedicated cluster has been effective for us.
Hey everyone. So yeah, the technologies that Ming just mentioned are very useful to do for performance isolation, but they don't solve all of the issues that we see. And so the issue that I'm going to be talking about today is something that inspired quality of service. So let me start from the beginning. About 2 years ago, when I first joined eBay, we were running some fairly large clusters with a pretty small team. To put some numbers on that, we were running 2 separate analytics clusters, around 2,000 nodes each, and we only had 2 full-time ops guys. So as you can imagine, it was pretty busy, and as a result, performance concerns tended to take a back seat toward keeping the cluster up in the first place. Now, we would have these performance issues. Basically, users would email us maybe one day every other month or so, and they would complain that HDFS operations would be very slow, right? Like simple HDFS operations could take many seconds to complete. And when this is happening, the jobs that you expect to take 10 minutes are now taking, maybe the entire day. So it's quite understandable that the users are upset about this. Now, a little bit of an aside, Hadoop is a fault-tolerant system. As such, it's very good at staying alive, right? So if a service fails, you have failover. If a process is killed, it'll be restarted. this is really good. Hadoop is really great at just chugging along. But there's some kind of bad side effects of this. The first is that you can have a lot of cases where the services are still up and pingable, but some other aspect isn't quite working right. And so if users can't really use the cluster, you can't really say your cluster's available, right? Another issue is that because of all this retry logic and such, it can be very difficult to determine the root cause of an issue. So if something's gone wrong, it can be masked by a lot of layers. Anyways, back to the issue at hand. There's this performance issue we're seeing, right? So what we do is we send an engineer to take a look at this issue, but by the time they have time to check it out, it turns out that the issue had resolved itself. And this happened many, many times. So for a while, this issue for us was just this annoying thing that happened, and it would resolve itself. You know, just another performance issue. Well, all of this changed when we suffered a show-stopping cluster outage from this issue. So what happened was the name node got so slow that data nodes were no longer able to connect, and we suffered cluster outage, which meant 8 hours of log replay. And this is 8 hours where no one could connect to the cluster at all. It was just total dead time. So after this happened, we started to take a serious interest in this issue. We really wanted to solve this. So, you know, how do you go about solving an issue like this, right? Well, you have to first understand what the root cause is. And there's a lot of ways you can do this. You know, a lot of you are probably collecting metrics, right, from the name node today. There's some interesting upcoming tools, such as name node top, that would make diagnosing this a breeze. But, you know, at the time, we used what we had, and we used audit logs. So for those of you who don't know, in HDFS, you can enable audit logging, and it will output to a log file the username, the operation type, the timestamp, etc. And we already had a process that would rotate these logs into HDFS. So at this point, we had already had terabytes of log files. And so now we want to do some analysis on these log files. There's naturally only one good solution for this, right? It's just to use Hadoop on it. So that's great. We can, you know, write a MapReduce job or use Hive or our favorite tools. And what we want to do is we want to compute velocity, right? The number of calls per unit time, let's say calls per hour. Because at this point, the prevailing theory, which is partially correct, was that this was caused by just overload on the name node, right? And that's a pretty good guess, given that, you know, if you have too many tabs open in your browser gets slow. If you run too many processes on your computer gets slow. I guess it's, you know, it's the same thing. So we did this analysis. We computed velocity per hour, and on top of that, we grouped by user, which turns out to be an important point. We did indeed find that there was a good correlation between a high velocity on a given day and complaints about cluster slowness. But what's more interesting is the nature of this slowness. So we have two graphs here. On the left, this is the normal cluster operation, what it looks like. If each user is a different color in this pie chart, the percentages are how many calls they are responsible for, right? So you see on a normal day, we have maybe like 12 big users of the cluster, and they're all using about the same share. On the right, there's a very different story, right? Oh, by the way, in that, on the left, there's probably like 100 users in the like small, you know, eating up maybe like a couple percentage points. So you have a few big users and a ton of small users. On the right, it's a very different story. You have one huge user consuming over 90% of the resources, right? You have another user that's consuming a couple percentage points, and you have everyone else kind of fighting for scraps over there. So this is interesting, right? That means you have one person solely responsible for the slowness of the cluster. And if you were to take away that one user, the yellow user there, you would find that the cluster behavior would just look normal. So that's good. That's good, right? So now we began to wonder, what is that one user doing, you know? What kind of crazy, iterative, machine learning, latest techniques are they using that would monopolize so many cluster resources? Well, it turns out that they were doing something like this, which is to say a whole lot of nothing. And, you know, we think they weren't doing it on purpose. We think, you know, either due to bugs in their code or unfamiliarity with the platform, they were writing code that just made HDFS calls, discarded the results, did it again forever, as fast as possible. And yeah, you laugh, but we found this, you know? And it turns out if you run this on a single machine with 100 threads or so, you can add 200 milliseconds of latency to the name node. And that may not seem like a lot, but consider that normal latency is sub-millisecond, right? So that means if your job used to take, say, a couple minutes, it's now going to take a couple hours. If your job used to take a couple hours on calls, it would now take a couple weeks. So you can see how this alone can blow it up pretty quickly. But of course, it gets worse. Because the whole point of Hadoop is distribution, right? We're going to distribute our code onto many nodes, and they're going to do the work. Well, if you distribute this code onto 1,000 mappers, what you're going to get is a distributed denial of service attack on your name node. It's going to hurt. Let's see how that happens. So on the right, we have a pie chart very similar to the one we saw earlier, where we have a ton of users. They're all using the cluster just about equally. As we spin up our bad job, as we call it, it starts taking up share in the cluster, right? It consumes more and more and more resources until we end up in a situation very much like the one we saw before on the right, where we have one bad user consuming 90% of the resources and everyone else fighting for that last piece of percentage. So this is, this is terrible, right? This is not what we want. And we began to wonder, why does this happen? Well, it turns out that this happens the fundamental way that the name node RPC service is designed. So let's dive into that right now. So all HDFS operations that are made, whenever you're creating a file, deleting a file, opening a file, renaming a file, listing directories, all of that stuff gets done through the RPC service. What happens is you have in your code, you're going to call HDFS.exists, let's say, on a folder. And the RPC client is going to take your information, it's going to serialize a protobuf. It's going to contain your username, the operation you're performing, and some parameters that you're passing. It's going to send that over the wire to the name node. The name node is listening usually by default, port 8020. It's got a ton of listener threads waiting for data. And as soon as there's data available, the threads are going to accept the data, and they're going to have reader threads create an RPC call object. This is basically the thing that gets passed around in the name node. The RPC calls are going to be put into a first in, first out call queue, very standard call queue. And as we're going to see later, this first in, first out nature of the call queue is what causes this issue in the first place. So it goes into the call queue. On the other side, we have a ton of handler threads. You might have maybe 100 handler threads or so. And they're just repeatedly waiting to grab the first available entry in the call queue and execute that entry. And so oftentimes executing the entry will require grabbing the name node lock. After it's done with executing the entry, we have responder threads that will send the response right back to the RPC client. And I mentioned earlier that normal latency is sub-millisecond. So this layer is very, very performant. Twitter has graciously shared some numbers with us today. Their name node sees typical RPC call velocities of 6,000 calls per second and peak velocities of 60,000 calls per second. And I can confirm that eBay sees similar numbers as well. So any slowdown in this layer is going to cause a lot of problems. So it's very important for this to be very performant. Let's take a closer look at this call queue, because I mentioned earlier that this is kind of where the magic happens. So it's easiest if I show an example. Remember those two apps from before, right? We have good users and bad users. They're going to make some RPC calls. So good user makes a call, right? And for each call that the good user makes, the bad user is going to make a ton of calls, because that's all it's doing, right? It doesn't have to do any processing or other work. It's just blindly making calls. And because it's doing that, for every good user's call, the bad user can make 100,000 calls. And so when the good user makes its next call, it's going to be behind 100,000 red-colored calls here, and so on. Now, when it comes time to process these calls, they're going to be processed in the order that they arrived. So the handler is going to take the green call first. Then it's going to take 100,000 red calls. Then they're going to take the other green call. And remember, if the peak processing velocity is 60,000 calls per second, Well, that's over a second of latency if you have 100,000 read calls between you and your next call. So this is why we have that issue. But it gets even worse, because what happens when the queue fills, right? Let's say the processing kind of gets behind and clients keep filling up the queue. Well, when the queue completely fills, the reader threads don't have anywhere to put their RPC calls, so they block. They just wait for the queue to have an open space available. Somewhere in the kernel, because things are no longer being accepted off the socket, there's another queue that fills up. And when that queue fills, no one can connect to the name node anymore. When this happens, they receive timeout exceptions, right? And this is really bad because not only can your clients not connect, but your data nodes also need to connect to the name node. And when your data nodes can't connect and send their heartbeats, the name node after a while thinks that the data nodes have died. So they begin scheduling block replication. Now, computing where to put new blocks is a very expensive operation. It can take hundreds of milliseconds. So now we have the name node trying to do block replication, which is slowing it down further, which is making the queue fill up even slower. And you can see how this quickly spirals out of control. And actually, this is how we lost the cluster in the original story. So solving this is definitely very important for us. Now, there's a few possible solutions out there that were existing at the time. HDFS federation, as Ming mentioned earlier, is a way to partition your cluster into different namespaces. And this helps in a way, but it also doesn't really solve the problem completely, because if you and the bad user tend to access the same files, you're still not going to be protected. So we don't consider this a complete solution. Another possibility is the service RPC feature in Hadoop. You can turn on the service RPC queue, which will create a separate RPC server that listens on a different port for all your data nodes to connect to. Now, this will protect your data nodes from dropping out due to this issue that I mentioned, but it doesn't save your users when you have one malicious user consuming 90% of the resources. It's still going to be slow for them. So this is also not a complete solution. Finally, there's been some work in open source around fixing the name node global lock. This is a very ambitious project, but even if we solved this and used fine-grained locking, it still would not completely fix the issue. We could still overwhelm the name node. So with that, I hope I've given a pretty good overview of the issues that we face, and Ming's going to talk about the solution that we came up with.
All right, let's look into the solution. So based on the diagnosis, we came up with two main requirements: fairness and performance. Processing RPC requests fairly among all the users with quality of service should address the core issue here. But we need to make sure there's no performance degradation, so the RPC layer can continue to process tens of thousands of requests per second. Now, people might point out that these requirements look similar to those found in other systems, such as how routers handle network traffic or how YARN scheduler manage the cluster resource allocation. And this similarity inspired us to model this as a scheduling problem. And the scheduling resource will be the RPC handler threads instead of memory, CPU, or network. For example, if the RPC server is configured to have 128 handler threads, there will be 128 resource units available for scheduling. Then we just need to make sure each user is given a fair share of the resource. Now, writing a complete scheduler from scratch is non-trivial. In addition, due to RPC layer's complexity and its impact on production services, we would like to make it easy to test, deploy, or roll back if necessary. And to achieve that, first, we want to provide good abstraction around this feature and make it easy for people to turn on or off the feature. Secondly, to simplify the design, we make certain assumptions, now some of which are not absolutely correct. For example, we know that some name node operations are more expensive than the others. But these assumptions allow us to quickly iterate through implementation and testings. And as it turned out in the end, these assumptions are reasonable enough to solve our problem. Lastly, given this is a scheduling problem, we would like to leverage any existing solution if they are available. And as it turned out that network router has solved similar problem, where it needs to make sure high data rate flow can take more than its fair share from the link capacity. And the solution there is to use fair queuing instead of FIFO queue. And that's the basic idea behind fair call queue approach. Instead of using a single FIFO queue, you use several sub-queues with different priority levels. So in this diagram, there are 4 sub-queues, with Q0 being the highest priority queue and Q3 being the lowest priority queue. Then as RPC requests come in, a scheduler will keep track of the call volume of each recently active user. And we use that data to compute the priority of each RPC call and assign the call to the corresponding subqueue. The higher the call volume, the lower the priority. Exactly which subqueue the call will be assigned to depends on how the call volume of that specific user compare with the queue configurations. For example, say a good user with 11% of the total call volume send a new RPC request. The scheduler will compare 11% with 12% threshold, which is the boundary between the highest priority queue and the second highest priority queue. Given 11% is less than 12%, the call will be assigned to the highest priority queue. Then a bad user send another RPC call. Then the bad user has 80% of the total call volume. The scheduler will compare 80% with 50% threshold, which is the boundary between the lowest priority queue and the second lowest priority queue. And given 80% is greater than 50%, the call will be assigned to the lowest priority queue. As a result, RPC requests from good users will be assigned to higher priority queues, and RPC requests from bad users will be assigned to lower priority queues. Then a multiplexer will pick up this call from the subqueue in a round-robin fashion and pass them onto the handler threads. And to make sure higher priority requests are processed sooner, each queue has a weight. It determines how many items the multiplexer will take from that queue before moving to the next queue. For example, say we configure these 4 queues with weights of 3, 2, 1, 1 respectively. Then the multiplexer will first take 3 items out of the highest priority queue. And after it's done, it moves to the next queue and take 2 items, and so on. After it scans through all the subqueue, it will go back to the highest priority queue and repeat the whole process. In the end, the scheduler and the multiplexer together will make sure RPC requests from good users are processed in a timely fashion. Now, to actually evaluate the effectiveness of fair call queue, we set up a small cluster, run a MapReduce job using the buggy code that Chris mentioned earlier. And that will generate lots of read requests to NameNode, and we want to evaluate its impact on a good user. X-axis here represents the time since the bad job starts, and Y-axis represents the RPC latency of the good user. The lower, the better. As the result clearly indicates, switching from FIFO queue to fair call queue greatly reduces the RPC latency of the good user. Chris mentioned before that if RPC queue stays full for too long, new application might not be able to connect to NameNode. And to solve that problem, we introduced back-off mechanism to the RPC layer, so that in the event of name node congestions, client will be asked to back off and retry at a later time. And here's how it works. Say a bad user fills up the lowest priority queue. Now, given other subqueues are not filling up, new requests from good users can still be processed successfully. But new requests from bad users will be rejected, with retryable exceptions thrown back to the client. And RPC client understands this type of exception. It will catch, retry, and succeed at a later time. The key takeaway here is, in the event of name node congestion, only the bad user will be asked to back off. And to evaluate the effectiveness of RPC backoff, we set up a cluster run a MapReduce job that keeps creating new directories in HDFS in the time loop. And that will generate lots of write requests. And we want to evaluate its impact on a good user. X-axis here represents the number of clients and connections of the bad job, and Y-axis represents the RPC latency of the good user. As we can see, when the number of connections is small, fair call queue alone is good enough. But when the number of connections go beyond 10K, the benefit of RPC backoff becomes clear. And when we reach 50K, new application cannot even connect to name node if RPC backoff is not enabled. So after months of testings and benchmarkings, we enable this feature on all production clusters at Twitter and eBay. The feature has been running reliably since, and we no longer have name node congestion problem. Given this feature is available in open source, everyone can try it out. And here is how. After you get the proper version of Hadoop installed on your cluster, you just need to find out the RPC port that name node listens on for application request. Most likely, it's configured to be the default number 8020. And then you just copy the following configurations, and you are done. Now, looking forward, there are a couple interesting things we can do to bring Hadoop QoS to the next level. For example, in the current implementation, we assume all users are equal. But in reality, some users are more important than the others. So a natural extension is to introduce weighted shares among all the users. And to support fine-grained quality of service at the HDFS layer, there are a couple of problems we need to solve. Name node today uses a global log to manage concurrent access to HDFS metadata. For a large cluster like what we have at Twitter and eBay, we are talking about hundreds of millions of objects, and this log becomes a performance bottleneck. HDFS federation is useful, but sometimes it's not enough. So community is working on fine-grained logging support in name node. Besides name node quality of service, we should also support quality of service for the actual data transfer. Now, some work has been done in the community to support congestion control at individual data node level. It will be good if we can add fairness to it so that network and I/O are shared fairly at both individual machine level as well as the whole cluster level. In summary, RPC QoS has been enabled on all production clusters at Twitter and eBay. The feature has been very stable, and we no longer have name node congestion problem. So we encourage everyone to try it out. Besides solving name node congestion problem, RPC QoS is also an important step towards achieving fine-grained quality of service at the HDFS layer. And finally, we would like to say thanks to all the folks who helped out during design discussion and code review. And that's the end of the talk. Thanks, everyone. Oh, by the way, both Twitter and eBay are hiring. So if anyone is interested in solving system problem like this, please come and talk to us. So there are 2 mics here. Feel free to use them.
Hi, thank you for the talk. If you don't mind sharing, how did you measure the RPC rate of access on the name node? At Twitter, you said you have 60,000 requests per second at your maximum throughput.
Okay. How do we measure that?
Yes.
Okay, so the question is, how do we measure the RPC throughput at Twitter? So we have, so Hadoop provide a JMX metric systems. And you can use any other existing metric system. You can, either the custom solution or available like Gangly or other solution, you can actually pull the JMX from name node. And then you can use that to accumulate the history data, and then you can figure out the rate of request. Okay.
So at the end of your last slide, you mentioned something about web HDFS for the future improvements, but I didn't hear you elaborate on that.
Okay, sure.
Yeah, one more back, I think. Yeah, HTTP-based payloads. Yeah.
Okay. So the question is, what does it mean here by support web HDFS payload? Hadoop, there are 2 main sources of traffic coming into Hadoop. One is the traditional RPC layer. Another one is a web HDFS layer that goes through the HTTP stack. The current implementations is enhancing the RPC layer. It doesn't take into account the traffic coming from the HTTP Jettis stack. So that's why it would be good if in the future we can consider both traffics to manage quality of service.
I imagine measuring RPC counts is also achievable by analyzing the log files, as you guys have done at eBay.
Measuring the RPC counts.
Counting them and laying them out over time. I imagine you guys were ingesting your log files into HDFS and using Hadoop to analyze to get your root cause.
There are many ways to do this, but that's definitely one way.
Sure. Your name node deployment, I imagine, was HA and not secondary. Are there any nuances with regard to this analysis that would be applicable to a secondary type of deployment versus an HA deployment?
I see. I can't really say much to that. I suppose if you did audit logging, when we looked at audit logs, if you did audit logging and you had HA enabled, there wouldn't be, or there shouldn't be much overlap between the two. So you could still do this by merging your data sets and sorting by date.
Enhancement of the scheduler in the RPC.
Oh, I see.
Are there any considerations that are applicable to a secondary type of arrangement versus HA?
Okay. So I think, the question was, are we doing anything special for name node HA, right? The answer is no to that, because currently in HA you only have one active name node, right? So it shouldn't matter. I mean, you can do your scheduling per name node. What might be interesting is what you're talking about is federation, right? Because the scheduling information is not shared per name node. But no, currently it is per name node.
Enhancement. So the question is, I think the extended question to that is, if this feature at RPC layer can be applicable to other services at Hadoop, like Resource Manager or other master service that has lots of requests per second. So far, we are seeing name node is the major problem we need to solve. We haven't seen any other instance where we need to apply this RPC layer enhancement for other services.
Sorry, too close. What sort of monitoring and alerting do you have around availability per user? I assume for your bad user, they're probably not malicious. They probably just have buggy code. You'd like them to know, and they'd like to know you have a bad job. It's going to languish in this queue forever. You should fix it. Do you have any way of servicing that to them?
Sure, yeah. So when you enable quality of service currently, in your JMX stats, you're going to get two additional things. The first is the fair call queue, which in addition to providing the queue length, as you get today, you're going to get the queue, the per sub-queue length. So you have an array full of numbers, which is the length per sub-queue. The second thing you get is the scheduler statistics. So the scheduler provides two pieces of information. First, it shows you what each user is scheduled, which queue each user is scheduled into, right? So you get like a JSON object that you can parse out, and you can determine who's in which queue. The second thing you get is the number of calls that the scheduler sees for each of these users. So if you were to record this information, right, you can monitor this information, and you can alert users that they're in higher queues, if you would like.
In terms of configuration, so the number of queues and the weight on the queues, is that configurable?
Yeah. So actually, we can briefly talk about this, even though it's the configuration is a little complex. We did provide some slides on this. So let's talk briefly about tuning, right? So you don't have to tune this because the defaults are pretty reasonable for most clusters. But if you have larger clusters or if you have a lot of users, it may be worth tuning, right? And just a note, you can actually refresh the call queue without failing over by running this DFS admin refresh call queue. So there's a number of things that you can tune, and they're all controlled by the same style of configuration keys. The first is the number of sub-queues, which we call priority levels. The more sub-queues you have, the more unique classes of service you have. But also it controls kind of the percentage that users cannot exceed. So if you have 4 sub-queues, users will start to be penalized after exceeding 25% share of the cluster, when things are really busy. If you have 10, it'll be 10%. So we run 10% at eBay, just for reference. Or sorry, 10 sub-queues. The second is the decay factor. The scheduler will decay its counts every once in a while to prevent overflowing its belongs, and this kind of controls how much are decayed by each sweep, and larger decays will decay more slowly, or larger values will decay more quickly. That's the typo. The second is the sweep period. That kind of ties into decay. The faster this is, the more responsive your scheduling is going to be. These thresholds, as Ming mentioned earlier, that there are thresholds between each of the scheduler queues. And these determine the kind of boundaries you have, right, for scheduling into different sub-queues. And this, this is all configurable. The weights control per multiplexer, and that controls kind of the aggressiveness of your QoS. So if you set it to be very aggressive, right, you have like drawing a lot from the first queue and very little from the last queue, it'll be more impact, right? Or you can make it all ones and you'll have the least impact. And this is for configuring the number of backoff attempts. So that was really, really quick. But if you have any further questions, you can ask over email or something, and I'd be glad to help. Yes, we will be sharing, I believe the conference organizers will be sharing these slides. Yeah.
All right, thanks a lot.